Okay. Akansha, please note the attendance.
Yes, ma'am.
Okay. Yeah. We have seen yesterday the first generation CT scanners, and with coming to the second generation CT scanners, there we had the narrow fan beam geometry. So fan beam, a fan varying in angle from 3 degree to 10 degree beam directions, and linear detector array up to 30 detectors to acquire more data. So you can see here there are multiple detectors which are placed linearly, and translate rotate movements of tube detector combination is here also, like what we have seen in the uh, other generation, and fewer linear movements are needed as there are more detectors to gather data. And so the fan beam, which will cover more area across the patient, and more information will be collected by the multiple detectors placed. So the movements across the linear direction will be lesser in the second generation. And between linear movements, the gantry rotates 30 degree, and only 6 times the linear movements got repeated. Scan time is approximately 20 seconds. So in the first generation CT scanners, the scan time used to be around 5 minutes, and here it is 20 seconds. So the X-ray beam is picked up by a row of up to 30 detectors, and the X-ray source and detector then move together. So this is same as how it was in the first generation also. The two then rotate together to image a different angle. This is repeated until a single slice is scanned. The two then move down the patient and start imaging a different slice in the patient. This method took 50 to 90 seconds per slice. So here you can see that the time of acquisition has brought down significantly over that by incorporating a fan beam as well as multiple detectors in the second generation. But the process of acquiring the images remains the same like the first generation CT scanners. And coming to the third generation, uh, here we have rotate, and the tube as well as the detectors rotate. Motion is completely eliminated. Translatory motion is completely eliminated. Pulse width, pulsed wide fan beam of 50 to 55 degree. There we have seen it was varying up to 10 degrees only. So we have a very wide fan beam which have the capacity to cover the patient body. And arc of detectors 600 to 900. 600 to 900 detectors aligned as an arc is utilized so that the whole fan beam the information passing through the patient could be acquired at the same time. Detectors are perfectly aligned with the X-ray tube. What does it mean? Like this arc is such that this detector is aligned perfectly with the beam direction as well as the focus of the X-ray. Scintillation crystal detectors can be used, and scan time is less than 5 seconds in the third generation. The X-ray beam hits a row of detectors wide enough to image the whole slice. So there is no rotatory motion required, and the two then rotate together to image a different angle. This is repeated until a single slice is scanned. Then the array is moved to a different slice for the axial scanning. Axial movement takes place to slice by slice scan in different directions. So across the patient, we don't need to, the translatory motion need not be there as the fan beam is wide enough to cover the patient, and the detectors are placed in perfect alignment with the X-ray tube, so that multiple detectors are placed so that all the information will be received properly. Alternatively, the detector array is continuously moved down the patient as it rotates. That is what is called as spiral scanning, when the detector array is continuously moved down the patient as it rotates around it. This is the most commonly used method today and takes around 0.3 seconds to image a single slice. And the ring move along the detector, that gives ring artifacts, which is the disadvantage of the third generation CT scanners. So here is the next generation, fourth generation CT scanners. Here you can see from the picture itself, the continuous wide fan beam 50 degree to 55 degree, which is able to cover the whole patient body. And the rings of detectors, more than 2000 detectors are there, which is placed in a ring around the patient and developed specifically for cardiac tomography imaging. The fourth generation CT scanners were specifically developed for cardiac tomography. And tube is rotating here. You can see the tube where the X-rays are produced, that rotates around the patient and the detector is fixed in the ring. The X-ray tube rotates in a circle inside the detector ring. When the tube is at a pre-described angle, the exposed detectors are read. So when the detector is at say 355 degree, these detectors will be read. And as the angle of the detector, the X-ray tube changes, correspondingly the other detectors will be detecting. And scan time is less than 2 seconds. This is not commonly used today, and this eliminates the ring artifacts, because in the previous one, since the detector array also moves along the slice by slice motion, so we had the ring artifact there. So here in the fourth generation, this was avoided. And the high cost was the major disadvantage of this. So here we can see the first generation CT scanner where parallel beam geometry was utilized, translate rotation motion was taken advantage of. And in the second generation CT scanner, we have fan beam and translate rotates. And in the third generation CT scanner, fan beam and rotate only, no translate. And in the fourth generation CT scanner, we have fan beam, stationary, circular detector. So this summarizes the first 4 generations. So here it is like how the yes.
Ma'am, what is circular detector?
Here you can see, the detector is, there are multiple detectors up to 100, 2000 detectors which are placed in a circle. You can see the circle here, no? Here, this red
Okay,
blocks,
ma'am. Yeah, understood.
yeah, yeah,
I
each are
thought
a
of
detector.
single detector.
No. These are multiple detectors. In the third generation, we had multiple detectors, fewer in number, but it was in an arc, part of a circle. So this arc needed to move while we acquire information. So here we don't need, in the fourth generation, we had a circle of detectors which is fixed and the X-ray tube moves, and when depending upon the position of the X-ray tube, the corresponding detectors will be read to get the information. So when it is at this angle, the detector, like say it is like 270 to say 120. So 120 to 270, these detectors only will be read. And when this comes here, so correspondingly, say from 120 to 300 or 310 will be read, like that. Like if you
Okay,
consider
ma'am.
it as a circle of 360 degree, so these only will be read when it is at this point. So as the X-ray tube rotates, the corresponding arc will be read. Here the arc or the detector need not move. Detector is fixed here. the other place the arc needs to move because it is only this much, no? Only this many detectors are there. This will keep on moving as the X-ray tube moves. That is the basic difference. So that is what is explained here. You can see the parallel beams in the first generation. And after that we have small narrow fan beam, and then we have wide fan beam, and then we have same wide fan beam there in the fourth generation also. And in the detector we have detectors placed across it. Then we have second generation may we have fan beam and the same detector translate rotational movement. And then here only the rotation, not the translation, as the wide fan beam is able to cover the translational area. And here it was only these many detectors. Here we have the whole ring available. So this is again the same thing represented in another pictorial way. So where we have single detector, multiple detectors, and multiple detector array, and stationary ring of detectors. So here also you can see the parallel beam and single detector, cone beam or fan beam, and multiple pencil beams, and then here it is fan beam, fan beam. And electron beam
Ma'am,
scanner, yes,
ma'am, in third generation, what you said, there is something
fan
phased.
beam, third generation. Phased,
Ma'am, in previous slide
yeah.
sir.
Which one? This one.
Ma'am, what is pulsed family?
Pulsed is the beam is, it is formed in the form, the total beam is formed in the form of pulsed beams. It is not a single instance the whole X-rays are coming out. So pulsed means, like, you know, the sinusoidal curve, no? The sinogram. We have a crest and we have a trough where the intensity is high and then the intensity is low, then the intensity is high, then the intensity is low. That is called a pulsed beam. We get it in pulses. So we can have, if it is a continuous one, then we will have sinusoidal spectrum, and if it is a fixed this thing, then we will have spectral lines type. Understood?
Yes, ma'am.
Okay. So, or in simple means, we can say that these beams, each ray you take it as a different one. So each one is produced as a pulse. Each ray is produced as a pulse. Then the next pulse, next pulse, next pulse, next pulse, like that the X-rays are produced. But all this happens in very short amount of time. And the whole scanning takes place in less than 5 seconds. Electron beam scanner is sometimes described as the fifth generation CT. An electron beam is deflected by an electromagnetic field onto a fixed array of tungsten anode target underneath the patient. The electromagnetic field sweeps the electron beam across the target, creating hundreds of X-ray beams firing through the patient to the detector above the patient. So fast scanning of 50 to 250 milliseconds, and mainly used for certain cardiac imaging. These were not very popular. So we have an electron gun, we have a deflection foil. So the electron gun will eject the electrons which will be deflected by the deflection foil to a tungsten anode which is placed under the couch, and where the X-rays will be produced, and then it will pass through the patient and detected by the detector above the patient. So this is electron beam Hello.
Yes, ma'am.
How are the X-rays produced in a normal X-ray tube?
When an electron beam hits the tungsten target
Yeah, where from the electron beam comes?
from the tungsten filament through thermionic emission.
Yeah. So here the electrons are produced by an electron gun. So that is the difference here. We do not have a complete X-ray tube here. So that X-ray tube is split into parts like that, where we have the source electron from an electron gun, not from a thermionic film, and that electrons are deflected. The electrons are deflected. You can see the electrons are coming like this. It is getting deflected over here to the target over here, which is under the couch. From here, the X-rays are produced and pass through, and then the detector above the patient will detect the uh, information from the X-rays, which are passed through the patient body. So this is another pictorial representation. Electron gun, large arcs of tungsten, targets and detector ring, and 17 slices per second. So this allows fast scanning. And why we need fast scanning for heart?
To avoid motion.
Yeah,
Cardiac motion.
yeah. So there is an inherent cardiac motion. So in order to achieve the imaging done within the cycles of that motion, so that the motion will not affect the imaging process. So that's why we need to have a fast so here we can see that like approximately 17 slices per seconds are acquired. And conventional CT studies were done in slice by slice mode. Patient was placed on the table and moved a certain amount into the bore of the gantry. Pulsing X-ray tube and detectors rotate 360 degrees, collecting data. Once complete, the patient and table were moved. Process was repeated for each slice of the procedure. And there is this slip ring technology. In the late 1980s, CT scanners with slip ring technology were introduced. The slip rings were placed inside the gantry. The slip ring technology allowed the tube to continue to rotate without the need for rewind. So in the previous generations, like we'll take the example of here. Here the X-ray tube is here. This has to rotate like this. So previously it used to be like, it never used to be a complete rotation like this, like 0 to 360 degree. It used to be like if when we have to take the acquisition for this much, it will say it will move from 0 to 180, then it will go back to 0, then 0 to 180 in the anti-clockwise direction. It used to be like that because like from the point from where the X-ray tube is, the cable needs to be that long to cover the whole distance, right? The X-ray tube has to move in this direction. It moves. So if the cable length needs to be so long. So initially it was not so. So it used to do like this. Take one arc, then go back, then take the opposite arc. So with the slip ring technology, it allowed to acquire the whole cycle in one go. So it did not rewind the cable to go to cover the full rotation. And continuous rotation of the tube and detectors coupled with continuous movement of the table and patient through the gantry are the basic components of spiral or helical CT. So the detectors are continuously moving. The X-ray tube as well as the detectors are continuously moving, and the patient on the couch will also move in order to acquire the images. So this is called a spiral CT, spiral or helical CT. The spiral CT collects the data for an entire volume of tissue such as the head or chest at one time. Scan time is reduced in that the start and stop time of the slice by slice scanner is eliminated. So previously one transverse axis, next slice, next slice, next slice it used to be, and with the help of the spiral CT, the couch also continuously moving, and the whole area needs to be covered is getting covered in one go. So you can see here a pictorial representation. So start of the spiral scan, it starts the cycle, it rotates around the patient, path of continuously radiating X-ray tube and detector. So then the patient body will be moving in this direction. As the patient moves
मैम
smoothly, yes,
मैडम एक चीज पूछनी थी
huh?
मैडम इन विच जनरेशन स्पाइरल सीटी कम फर्स्ट
No, this will be after 5th generation.
ओके
So as the patient moves smoothly through the gantry aperture, so that is the Z axis, the tube and detectors continuously travel around the patient, creating a spiral path. So this is called a spiral path, and that is hence the name spiral CT or helical CT. So third, fourth generation plus slip ring technology plus helical motion is what is called a sixth generation. So we generally talk till fourth, like we have till fourth generation where the acquisition time changed, and then like in third we had circular detector, and we had arc and fan beam, and in the fourth we had arc and circular detector along with the slip ring technology plus helical motion. Slip ring technology allows the continuous rotation along the circle, and helical motion allows this motion. So all these together we can call it the sixth generation. So this is in the early 90s. And the advantages are this allow the 3D acquisition within single breath hold. Volume set of data is 3D. We know that in the fourth generation, we had the fast sequencing for cardiac imaging. So that aspect is also taken in here. So the allow the 3D acquisition within single breath hold, and volume set of data is 3D. Simultaneous source rotation, table translation, and data acquisition. So the source and detector are moving, and the table is translating, and data is acquired at the same time. So for the data acquisition, it takes only 1 second per slice, and reducing scan time and improving the image quality. And this got introduced in the 80s to 3 rings, make connectivity to X-ray generator, detector and control signals, makes the rotation faster. Slip ring is used in spiral CT or multi-slice CT, allows the gantry to rotate continuously. You can see the gantry is rotating continuously. It eliminates the need of electrical cables which restrict the continuous rotation previously. High power X-ray tube is utilized, and oil cooling thermal system around the tube. So what we are achieving is a volume scanning in single go. Coming to the 7th generation, this uses multi-detector array. The collimator spacing is wider and more X-rays are used in producing image data. Opening up the collimator in a single array scanner increases the slice thickness but reduces spatial resolution in the slice thickness dimension. Hence, slice thickness is controlled by detector size, not by the collimator. Has better efficiency for patient imaging, and detector pitch needs to be defined. So we will discuss about these parameters. Multi-slice CT or MSCT was started in 1992 with two parallel bank of detectors that gives two slices. In 1998, solid-state multi-row detector was introduced to make 4 slices in each rotation. And multi-slice CT, previously we were taking slice by slice images. So in spiral CT, we had a continuous acquisition of slice by slice images. And here we have in one go, we are acquiring multiple slice information. And multi-slice CT generally uses third generation CT with helical scanning and low voltage slip rings. Rotation is faster, reduce the examination time, and MSCT with multi-detector array employs third generation CT with 16 detectors. We know that the initial it is 16 detectors, then 64 detectors, 128 detectors. So all these things we know commercially which are available. So that reduces the time taken for acquiring the fixed amount of data. Instead of collecting the transmission data for one slice each time tube rotates around the patient, accomplished by opening up the X-ray beam along the Z-axis, direction from head to foot, and having a detector array with 4 to 64 plus rows. As the number of slices being imaged per revolution increases and the X-ray beam is opened, it goes from being a fan beam to a cone beam. And however, spiral MSCT allows overall improved image quality with faster scan time and the ability to perform additional procedures such as CT angiography and cardiac imaging. So here you can see multi-slice spiral computer tomography. Previously it was a single spiral. Now multiple spirals are going on. Here you can see 1, 2, 3, 4 in different colors. So there are 4 spirals around the patient. Having multiple rows of detector results in 4 or more slices being imaged during each revolution of the tube. One second. So here it eliminates interscan delays, required continuous rotation by the low voltage slip ring. And slip ring passes electrical power to the rotating components, X-ray tube and the detectors without fixed connections. So a slip ring is a drum with grooves along the electrical contractor brushes inside. Data transmitted from the detectors via various high-capacity wireless technologies, thus allowing continuous rotation to occur, and a slip ring allows complete elimination of interscan delays, except for the time required to move the table to the next slice position. So as we were discussing here, this is a CAT scan of slip ring. So there are grooves along which the detector and the X-ray tube rotates, and it is not connected by cables. So the power supply is given to the detector as well as the X-ray tube by these slip rings. So it is kind of a wireless technology. So it does not require time for continuous rotation to occur. It can smoothly pass on from one arc to the next arc. So we can represent the slip ring like this. So the sliding power supply data and control signals, sliding contractors, and the X-ray tube and the detector arrays are moving inside that slip ring.
Ma'am, what material is slip rings made of?
It can be any metallic thing which helps in conducting the electricity. I don't know exactly what material it is made of. I can find out before the next class if it is available information. And different companies will have their trademark material for that. So that is not of much importance when we study about the CT scanners. But anyway, I will find it out. It can be any conducting material with unflexible material, like how we are looking at it. The machine, the X-ray tube and the detector array should be able to smoothly pass over, at the same time receiving the required power supply from that. So this should allow the electrical contact to remain, and at the same time movement is without any boundary of the cable length or time for rotating and all that, moving from one position to another and all. Only problem here, not the problem, the time is consumed for from slice by slice information, the translational movement, how much time it takes from for the translational motion, that actually takes the time for the imaging. So this is this is the we have seen this image. It is also called volumetric helical or spiral scanning. Allows for the tube and detector components to spin continuously in a non-stop rotation sequence. Can scan whole body segments in one breath hold. So here is the picture. So typical slice plane. So the darker line here is one slice. So in helical CT, improved body CT was made possible with advent of helical CT. Patient table is moved smoothly through the gantry as rotation and data collection continue. Resulting data from spiral path relative to patient slices at arbitrary location may be reconstructed from these data. Certain concepts associated with helical CT are fundamentally different from those of axial scanning. One such concept is how fast the table slides through the gantry relative to the rotation time and slice thickness being acquired. This aspect is referred to as the helical pitch and is defined as the table movement per rotation divided by the slice thickness. So here is what is pitch. So this is a term used especially in helical CT. It has two terminologies depending on whether the single slice or multi-slice CT scanners are used. In multi-slice CT, the pitch influences the radiation dose, image quality, and scan time. The pitches are the collimator pitch and detector pitch. So you can see that the how fast the table slides through the gantry relative to the rotation time and slice thickness being acquired. So this aspect ratio is referred to as the helical pitch. So this can be defined as the table movement per rotation divided by the slice thickness. So one rotation की time में how much the table moves divided by the slice thickness. So the two different types of pitches are collimator pitch and detector pitch. The pitch is the parameter without units that provide information about table travel relative to beam collimation. It is defined as table travel per gantry rotation to beam collimation. So here the pitch definition in multi-slice CT. So pitch table travel per rotation divided by X-ray beam width, and pitch D is table travel per rotation divided by detector width. Here you can see that this is the X-ray width and this is the detector width. You can see one black square, dark square here. This is the detector width and this is the beam width. So how much the table moves in one rotation divided by the beam width is the pitch X, and pitch D is the how much the table moves in one rotation divided by the detector width. So beam pitch is 1 by I by W, detector pitch is I by T, and beam pitch is detector pitch divided by N. So I by N plus T. So the single detector array, I is the table travel mm per rotation, and W is the beam width in mm, and T is the single data acquisition channel width, and N is the number of active data sequence acquisition channels. So I think everything is explained over here. So the table travel expressed in mm per rotation is I. Beam width, you know clearly what is beam width, and then the single data acquisition channel width T. This is the single data acquisition channel width, and N is the number of active data acquisition channels. Kitni active acquisition data channels are there at one point of time. For single slice, the table travel per rotation divided by the image thickness. If table travel greater than slice thickness, pitch is greater than 1. And if for multi-slice, table travel per rotation divided by total active detector width. So this corresponds to the X-ray beam collimation, the star sign. The total active detector width corresponds to the X-ray beam collimation. It is clear from here, right? So here we have single detector array. So the beam width over here, and here in one beam, how many detectors are actively involved in the detection of images. That is what gives us the multi-detector pitch. Sorry. So here are some examples. Table travel per rotation is 7.5 mm and image thickness is 5 mm. So the pitch will be 1.5. And for multi detector scanning, the table travel per rotation to 7.5 mm and 4 images with thickness 2.5 mm. So pitch is 7.5 divided by 4 into 2.5. So that is 0.75. So that is the advantage of multi-detector. So some more examples. If the slice thickness is 10 mm and the table moves 10 mm during one tube rotation, then the pitch is 10 by 10 or 1. If the slice thickness is 10 mm and the tube moves 15 mm during one tube rotation, then the pitch is 15 by 10, which is 1.5. And if the slice thickness is 10 mm and the table moves 7.5 mm during one tube rotation, then the pitch is 7.5 divided by 10 or 0.75. So you have understood the calculation. So what does it mean? So in the first example, the X-ray associated with consecutive helical loops are contiguous, that is, gaps between the beam and no overlap of beams. No gap,
Ma'am, there is a
and in
network
the second,
issue
which is
from your
1.
side.
Exists between X-ray beam edges of consecutive. Huh?
You were not audible. Your voice
Hello?
was breaking. Your voice
There
was
was a
breaking.
network issue
I
from your
didn't hear
side.
you.
Ma'am, there was a network issue from your side, and we were not able to hear you.
Okay. Okay. So the calculation you understood, like different calculations for different table movements and the tube rotation, and the slice thicknesses. So the meaning of that, what happens, what is the meaning of saying that the pitch is 1? So that is what is in the first example. The X-ray beam associated with consecutive helical loops are contiguous, means there is no gap between the beams and no overlap of beams. Between two beams, there is no gap and beams are not overlapping also. It is one adjacent to the next, like that the beams, the X-ray beams are going. And in the second example, a 5 mm gap exists between X-ray beam edges of consecutive loops. So one loop to the next loop, the X-ray beam have a 5 mm gap. In the third example, the beam of consecutive loops overlap by 2.5 mm, thus doubly irradiating the underlying tissue. The choice of pitch is examination dependent, involving a trade-off between coverage and accuracy. So that you would have understood. When we are taking G scanners have unique property of forming images with particularly good quality at two specific pitch values, HQ and HS. And the image formation includes the collection of projection data. These data are not all at same table position. So synthesize a set of projection data via interpolation. Interpolate between views taken at the same projection angle but different table positions. Then use filtered back projection on synthesized planar data. So use data 180 degree each side of reconstruction position. Introduce artifacts where structure changes along the Z axis. Here the diagram of a helical data interpolation is shown. So the path of continuously rotating X-ray tube is the dark sinusoidal curve seen here. The X-ray tube as well as the detector is rotating around the patient. And the selected image plane, any plane which is selected. So here, how the interpolation takes place. You can see that this is the plane. So this point and this point contribute to the information here. And this point and this point contribute to the information here. This point and this point contribute to the information here. And this point and this point, this point and this point, this point and this point. This corresponds to the information here. So the patient, what we have to keep it in mind is the table is moving correspondingly. So it will have same information is acquired at different cycles. The 7th generation uses multi-detector array. The collimator spacing is wider and more X-rays are used in producing image data. And conventional single slice CT has one X-ray tube and a single row of detectors. And the detector row contains 500 to 900 detector elements. In contrast, multi-section CT has one X-ray tube and multiple rows of detectors. Along the longitudinal axis of the patient, each row has 500 to 900 detector elements, and many rows together create a two-dimensional curved array containing thousands of detector elements. which are connected to separate data acquisition systems generating multiple channels of separate data. In the multi-slice CT, the X-ray bundles not only fan out within the gantry plane but also diverge from the gantry plane. This imaging geometry is called the cone beam imaging geometry. The multi-slice CT was started in 1992 with two like this we have seen. I think this is a repetition of the not exactly a repetition. So the multi-slice CT was started in 1992 with two parallel bank of detectors that gives two slices. And in 1998, the multi-row detector was introduced to make 4 slices in each rotation. And the multi-slice CT generally uses third generation CT with helical scanning and low voltage slip rings. Rotation is faster, reduce the examination time. And multi-slice CT with multi-detector array employs third generation CT with 16 detectors. So instead of collecting the transmission data for one slice each time, tube rotates around the patient, accomplished by opening up the X-ray beam along the Z-axis, and the number of slices being imaged per revolution increases and the X-ray beam is opened. It goes from being a fan beam to a cone beam. However, spiral MSCT allows overall improved image quality with faster scan time and the ability to perform additional procedures such as, okay, this is a repetition of the slide, sorry. The diagram showing the concept of dual pitch. So it is 20 mm X-ray tube, X-ray beam, and 20 mm rotation, 20 mm rotation table travel per rotation table travel. The table moves 20 mm in one rotation of the X-ray tube, and the X-ray tube is or X-ray beam is of 20 mm, and we have 5 mm detector. So we have 4 colors here. Pitch is or the pitch is 20 by 1 and the 20 by 5 which is 4. And clinical advantages of okay. Think we'll stop here for today. We'll discuss the remaining thing in the
You
next
put down the phone